All right, welcome back to EC 3030. And we have done the first midterm last week, and we are still grading the midterm. So we will update you with the solutions later, and we'll discuss about the questions in lecture in more details later. And today we are going to continue our technical discussions. But before that, since we are near the midterm of the semester, so I'd like to take this opportunity and have some of your feedback. So this is the midterm survey created under the quiz, and you are encouraged to complete this anonymous survey before the Sunday. So please share your feedback based on your lecturing experience and the homework and the exam experiences. So this will help us to improve for the rest of the semester. All right, so any other questions before we start? So since the learn before the first midterm was about 2 weeks ago, before we discuss the new materials, I think it's good to have a quick recap of the lecture 9, where we talk about the MOSFET IV characteristics. So we use NMOS as an example here, and we have the physical structure of NMOS shown here. The substrate is P-type silicon, and source and drain are N-type doping. And the oxide is insulator to separate the gate and the substrate. The circuit symbol for the NMOS is shown here, where we show 3 terminals here. And the MOSFET, in principle, is a gate-controlled current switch. So we need to apply the gate voltage Vg to turn on the transistor to allow the current flow, in this case, from the drain to the source. So this is the circuit symbol for the NMOS. And then we discuss how the current flow in the NMOS. So basically, we need to first create the channel by applying the gate voltage larger than threshold to invert the channel from the P-type to N-type. And then when we apply the drain voltage, the electron can flow, and then we can have the drain current. So we spent quite a few slides here to derive the IV equations. I will skip the derivation, but jump to the conclusions we have here. So this is very important equations. And we have 3 operation regimes. This is for non-channel transistor, where we have this ideal square law model. The first region is this cutoff region, where the gate voltage is smaller than the threshold voltage, and we say that the current is almost 0, because here the channel is not formed yet. This is true for the first order consideration, but today, in the lecture 10, we are going to correct this. We are going to say that this current is not exactly 0, but there are some finite current flowing, and we are going to discuss that in more details today. And then the second region is this linear region or triode region. This is when the gate voltage is larger than threshold, but the drain voltage is small. Let's say smaller than the Vg minus Vt. So here then we have this equation to describe the drain current as a function of both Vg and Vd. Of course, we have those coefficients in front of the voltage terms. Those coefficients are the mobility, the gate capacitance per unit area, and then the W over L, those geometrical parameters. So here, when the drain voltage is small, then we can ignore the second order term here, and then only look at the first order term. So this is like a linear relationship between the ID versus VD. So it's like a resistor. So that's why this is called a linear region. And then we have this saturation region where the drain voltage is larger than the Vg minus Vt. So for this non-channel transistor, this ideal square law model will predict the drain current now is proportional to the Vg minus Vt squared, and is independent of the Vd because it becomes saturation. So these are the equations, but also we can visualize the equations into this plot. First one is IDVD plot. We have a bunch of curves here. This is drain current versus drain voltage. Different curves correspond to different Vg. The larger the Vg, then the higher the current. And then we have the separation between the linear region and saturation region, and this is a boundary. And those turning points are the Vd set. Then this Vd set is determined by the Vg minus Vt. And in this first order equations, the saturation is really saturates the current, so it's flat. And then when the voltage is small, I mean the drain voltage is small, then you can use the slope of this curve to represent the resistance of the channel. So that's why you can approximate the transistor as a resistor because it's like a straight line. So this is IDVD, and also you can draw the IDVG. And here this is the threshold voltage. Below that is the cutoff. And above that, first you go through the saturation and then linear. And this is the turning point. Again, Vd set equals to Vg minus Vt. And then we talk about the MOSFET operations from the band diagram's point of view. So what is important is the band diagram along the channel direction, that is from the source to the drain. And you know this is NPN. So you have two PN junction back to back. And then we have this potential barrier between the N and P. So this barrier, especially between the source and channel, is important because that will determine the electron flow. So if without the gate voltage, this barrier height may be large enough, so there's no electrons that can jump over. So that's why the current is almost zero. But when you apply the gate voltage, then you are going to push down the band under the channel. So then the barrier height between the source and channel will be reduced. Now, especially when you apply the drain voltage to further bend down the drain band edge, then you have this shape of the band diagram. So then when you reduce the barrier top by applying gate voltage here, then more electrons can move over the barrier, and then they can be accelerated by the electric field, because here you see the slope. The slope in the band diagram means the electric field, as we discussed before. So these electrons will be accelerated. It's like water falling down. So those are the drift currents, and the electrons will be collected by the drain. So this is the operation principle from the band diagram point of view. So basically, the transistor is a gate control device, and the gate controls the barrier height between the source and the channel. So if you apply gate voltage, you are going to push down the band, and then more electrons can move over. That means larger currents. So this is the band diagram point of view of the MOSFET. And then we look at the actual IDVD curve from the real device. For example, here the device with a L, like 100 nanometer. So this is kind of a short channel device. This is more than 10 years ago, but still is representative. So you see that the IDVD curve, when you are reaching the saturation region, then the current no longer saturates. Still, current will gradually increase with increasing of the drain voltage. And we will discuss more details what causes this. This is due to the short channel effect, and we are going to discuss that in more details later today and the following lectures. Any questions? Hope you can remember what we discussed before, and then we are going to move to a new lecture today. That is lecture 10. So lecture 10 is about the subthreshold current. So what is subthreshold? Subthreshold is the cutoff region where the gate voltage Vg smaller than the threshold voltage Vt. And we talked about before the current is almost zero, but today we are going to look at the exact solution for the current in the cutoff region. So this is a reference chapter and the recorded video from the last spring and also Professor Asif Khan. Okay, so let's look at the MOSFET as a switch. Ideally, we want the MOSFET is a gate-controlled current switch. So you apply the gate voltage and then you control the drain current. So in this ID versus Vg plot, then we care about the Vt, the threshold. Ideally, you want the current to be zero below the Vt, and then above the Vt, you turn on the switch, and then current is in the on state. This is ideal switch, and if you think about like a light switch, you turn on and off, you will completely conduct the current or open the circuit. So then this is the ideal switch. But in reality, we have seen the IDVG plot of the transistor. It's unlike this abrupt, sharp transition at the threshold voltage, but actually it's a gradual process, right? So here, this is the threshold voltage, for example, 0.5 volts in this case. And above the threshold, as you ramp up the gate voltage, then the drain current will gradually increase following the equations we derived in the last lecture. So it's unlike the ideal switch here. But still, we have this turning on point where the current will be noticeable when the gate voltage is larger than threshold. So the question for today is here in this region. This is a subthreshold or this cutoff region. So we say that the current is almost zero, but today we are going to make it more accurate. We will say this current actually is non-zero. So what is the current exactly here? So we are going to look at the IDVG plot in a different scale. So here this is the linear scale as we typically see. You draw the current in the linear scale like 200, 400, 600. So it's equals a step in between. But if you want to visualize the small values here, because it's very small, then it's better to use this log scale to see small numbers, because a log scale can help you to visualize the small values. So if we draw the log scale of the same curve, then we are going to have this kind of results. So this is in the log scale, because here we have, for example, 10 to the power 0, 10 to the power minus 5, or minus 10. So this is like 5 orders of magnitude difference, or 10 orders magnitude difference. So it's very small number, but it's non-zero. So here the point is that below the threshold voltage here again, like 0.5 volts, the current is non-zero. You still have some current, but it's very small. So this is called the subthreshold current. And if you look at the bias condition for the transistor in this case, so first of all, the gate voltage is smaller than the threshold, so that's why it's sub-threshold. But still you need to apply the drain voltage. Drain voltage is larger than 0 to get the subthreshold current. If the drain voltage is 0, then the current is 0. There's no question about that. Because if drain voltage is 0, then source and drain equal potential, then there's no reason for current to flow. But here, what we are talking about is when the drain voltage is larger than 0, but gate voltage smaller than the threshold. So then this current is what we show here in this circle, which cannot be visualized in the linear scale here. So this is the I subthreshold. And we are going to talk about this in more details in the next couple of slides. But before that, any questions? All right, so let's look at what causes this subthreshold current. So to understand the subthreshold current, then it's better to look at the band diagram again, from the source to the drain. And this is source, this is the drain. And then in the middle we have the gate region, which the channel, also the channel region. So here we have this two back-to-back PN junction, and we have this barrier height, the built-in potential barrier. And the subthreshold, where the gate voltage is small. So gate voltage is small. So this barrier height is still high compared to the, let's say here we have the saturation. For example, that means the Vg larger than Vt. So this barrier height is small. So in the saturation region we discussed before, right? We have a lot of electrons in the source, and then now this barrier height is small, so a lot of electrons can jump over the barrier, and then they can be collected to the drain, and this is by the drift, because we have the slope, that means electric field, and then electrons will fall down like the water. So this is a drift current, and the current above the threshold is dominated by the drift current. But under the subthreshold condition, the drift current is small. So the major current component is this diffusion. So diffusion current dominates below the threshold. So why diffusion? So here, since this barrier top is still high, then the channel is not inverted yet. So you still have the NPN. So the source has a lot of electron. Channel has much less electron because it's p-type still. So electrons tend to diffuse from high concentration source to the low concentration region like the channel. So we have the diffusion. And the diffusion, again, is to move over the barrier top here. On the other side, from the drain, also you may have some electrons that can diffuse over this barrier top. So we have the electron flow, let's say I plus, from left to the right, but only for the electrons that are above the barrier top and diffuse over. And also from the drain side, we will have the electrons that diffuse over, but the probability is less. because here if you consider the Fermi function, and the Boltzmann approximation tells you it's an exponential decay in terms of the probability of the electrons with higher energy. So here only the shaded region. That means those electrons can move over the barrier from the left to the right. But for the drain side, because we apply the drain voltage push down the Fermi level of the drain side. So then the shaded region here is much less because this is exponential decay function. So this shaded region is much less. That means much less number of electrons can move over. Or in other words, from the right to the left, you see a higher barrier. So those two diffusion components are not equal, right? Are not equal because from the left to the right, you have more electrons, and from the right to the left, you have less electrons. So there's net current flow, and that is the subthreshold current, and that is dominated by this diffusion. So any questions here? I got one question. So just going back to the recap a little bit, applying VG creates channel, but actually applying VD is what creates current flow across the channel, correct? Yes, that's correct. So first you need to apply VG to invert the channel from the p-type to n-type. But if the VD is 0, then there's no voltage potential difference between source and drain. There's no current flow, even though the channel is inverted. Only when you have the VD, then you create the potential difference between source and drain, then you can have the current flow. Okay. Then let's look at the diffusion current here. So the diffusion current is proportional to the electrons that are above the barrier top, like this shaded region. So this one is modulated by the surface potential. So what is surface potential? If you recall the surface potential, phi s. So phi s is how you bend down the band, the EC. If you think about without the gate voltage, maybe the barrier height is something like this. Barrier is like this. But with the gate voltage you applied, it's smaller than Vt, but still you applied. Then the phi s is the bending down of the band edge by this phi s. And you can imagine that if you have more bending, then this shaded region will be larger, exponentially larger, because this is an exponential function here. So basically this phi s determines this exponential function. And let's assume that the electrons that is proportional to this q phi s over kt, exponentially dependent on this because it's an exponential function. And then on the drain side, the electrons above the barrier top will be less, will be this q phi s minus Vd over kt. This is because not only you have this phi s, but also this phi s needs to be minus by the Vd because you have less probability because of the Vd. So you have to minus the Vd here. This is this is at the source. This is at the drain. So the current is proportional to this. So we can express the current similar as this. I0 is a constant coefficient for Q phi s over Kt. This is the current from the left to the right, and then we have the current from the right to the left proportional to this electrons at the drain side that are above the barrier top. So you have this Q S minus Vd over Kt. And you know the net current will be the difference between those two. So this is what we are interested in, because this net current gives you the subthreshold current. Okay, so let's do that. So this net current is the difference between those two, and we have this I plus like this one, I minus like this one. So we just do the subtraction. And you can extract the common terms out. So what is common is this Q phi s over Kt is common between those two, and they have 1 minus exponential. What is left? Minus sign here, Q phi Qvd over Kt. So this is what you have here. This is the drain current ID. So if we write it here, so this is same as the previous slide. So this is when the gate voltage is smaller than the threshold. And we say the drain current exponentially depends on the phi s, that is the first surface potential, and also it may depend on the drain voltage here. So what is the phi s? If you recall in the lecture 8, phi s is the surface potential. And when we talk about the gate voltage we apply here, if you think about the gate voltage in the transistor structure, you apply gate voltage. The gate voltage and your body is grounded. So this gate voltage needs to be dropped across the VOX, that is the voltage across the gate capacitance, and then the phi s, which is the voltage potential at the surface of the silicon. This is your phi s, right? So you have voltage drop on the VOX and phi s. This is from your lecture 8. So we want to know the change of the phi s respect to the change of the gate voltage, and actually it's a voltage divider between two capacitance. Those two capacitance, one is the COX, that is the gate oxide capacitance. The other one is the C depletion of the silicon. If you recall the depletion region of the silicon, then you have the C depletion. So basically it's a two voltage divider. Two capacitor for the voltage divider. And then the gate voltage you apply, only part of that will change the phi s. Or in other words, if you recall the Venn diagram of the MOS structure, if you recall lecture 8, the MOS structure, you apply the gate voltage here to bend down the band, and then this phi s is the bending down of the surface band edge. But this Vg is larger than the phi s because part of the gate voltage dropped down the VOX. So if you change the gate voltage by 1 volt, maybe only 0.6 volts will be applied to the bias. So the bias respect to the Vg, there's a ratio. And this ratio is called the body factor. And we use M to represent that. Or in other words, the bias will only be affected proportionally to the gate voltage Vg. So let's say above the threshold voltage, you apply the gate voltage. Only part of the gate voltage will change the bias. And this factor is called the body factor. Alright, this is not above the threshold because here we are talking about the subthreshold. This is below the subthreshold, so this is a negative term actually. So here we want to replace this bias respect to the Vg, because eventually we need the ID versus Vg, because Vg is what you applied externally, bias is something internal to the structure. So if we replace the bias with this Vg, then we can replace the current equation like this. You just replace the bias with this 1 over m Vg minus Vt, then you get this equation. So in this equation, you will say you have this Vd, the drain voltage, but in practice, the drain voltage is typically much larger than this At over Q, that is the thermal voltage. At the room temperature, you know this is 26 millivolts at the room temperature. So typically your drain voltage can be larger than that. So that means this term is, let's say this x, if this is x, this x is much smaller than 1. Much smaller than 1. So if this is much smaller than 1, you know this is exponential function to the negative side, then it's approaching 0. So this one is approaching 0. Or in other words, you can cancel, or not cancel, I mean ignore this term. So what is left is only this one. So this is the equation we want to derive. A drain current only depends on the gate voltage, and this dependency is the exponential function. And I0 is the current here at the threshold voltage. Still, this is your threshold. And then below the threshold, this Vg minus Vt will be negative. So it's an exponential decay function. And since we draw this in the log scale, if you draw in log scale of an exponential function, you get straight line. And this slope is determined by this m kBt over q. So this is a straight line, and the straight line will have the coefficient in front of the gate voltage, that is this m kBt and q. So I don't require the derivation of the equation here, but I want to know the conclusion we draw here. So that is, below the threshold, the drain current exponentially depends on the gate voltage. And if you draw in the log scale of the drain current versus the gate voltage, you will have this straight line below the threshold. Any questions here? Why do we call them I plus and I minus? Okay, so this is just to, you can call it I left to right, and then this one I right to left. So plus, we just think this is flowing to the right, and minus, we think this is flowing to the left. So plus just means flowing to the right, minus just means flowing to the left. There's no particular reason why we call it plus or minus. So basically, two directions of the current flow, and the net current is the difference between those two. Why is it important to talk about this? Okay, I will have that in the next few minutes. This is very important, this subthreshold current. I will tell you why. Just stay tuned. Okay, so again, one more time on the conclusion. The drain current exponentially reduce below the threshold voltage, but it's not zero. It's very small, but it's not zero. Okay, this is an exponential function here. Of course, this is when you have the drain voltage. Your drain voltage should be above zero. Otherwise, if your drain voltage is zero, then the current is zero. There's no doubt about that. But this happens when the drain voltage is larger than zero, but the gate voltage smaller than threshold. Okay, so we are going to correct the IV equations before, and this is what we have before. This is ideal IV equations. If we only consider the first order effects of the transistor, then we have those ideal equations. And we call it a square law model for the non-channel transistor. But when we consider subthreshold currents, this is like a second order effect. Then we are going to introduce this one below the threshold. And of course, this will be added up to the current above the threshold as well, because those currents are independent because of two mechanisms. As we discussed before, this subthreshold current is caused by the diffusion. And what we derived before on this, for example, the current above the threshold, no matter linear region or saturation region, those are drift currents. So those two currents are independent mechanisms, so you can add them up. But I have to say that above the threshold, this drift current is orders of magnitude higher than the diffusion current. So in practice, we can always ignore those above the threshold, because this drift current may be 10 to the power 6, 10 to the power 7 times larger. So in practice, we can ignore that above the threshold. Okay, so this is a subthreshold current. And why is this important? Okay, let's talk about why this is important, since you asked this question. So this subthreshold current will determine the transistor's specs, especially the off-state currents. So here we show this table, summarized the practical parameters in different technology nodes. For example, from 19 nanometer introduced in 2003 to 22 nanometer introduced in 2013. Of course, we didn't show the latest technology node, which we are going to discuss at the very end of the semester, the last lecture on the advanced technology today. But for those practical technologies, we are always going to have this on-current and off-current parameters, and of course the supply voltage VDD. So here we have these definitions for the transistor's specs. Those specs are important for the circuit designers who design the practical circuits for the digital computers. those circuit designers need to look at the device parameters, and here are the important parameters, that is the on current density and off current density, I on and I off. So it's represented in the current density, that is the microamp per micrometer. That means we normalize the current ID, use the width of the transistor. For example, if the transistor is 1 micrometer, then how many microamp you can conduct the current. So this is the current density. And this is important design parameters for the circuit designers. Oops, current density. So here's the definition. Okay, if you have the power supply voltage VDD with your chip, then the on current density I on is defined as a drain current when the gate voltage and the drain voltage both are VDD. So that is the maximum current you can get from one transistor, because both gate voltage and drain voltage equals to the power supply VDD. And the off current is defined as the gate voltage equals to 0 and drain voltage equals to VDD. So the only difference is that you change the gate voltage between the 0 and VDD, and you have to keep the drain voltage to be VDD. So for example, here we show one practical IDVG curve in this log scale of the currents. So the I on, the current density, is here. If the VDD is here, then this is the maximum current you can get. In this example, it's like 1800 microamp if the transistor width is 1 micrometer. I think this corresponds to like 32 nanometer process. And then the off current is where the straight line here in the log scale intersect with the 0 gate voltage. And this is the off current. Okay. This is when the VD equals to VDD, and in this case like 1 volt. And the I off is 0.8 microamp if the transistor is 1 micrometer wide. So you see this on-off ratio is more than like 2000. So like orders of magnitude difference between the on and off currents. You want this as large as possible. For ideal switch, you want on to be very on, off to be open circuit. But as I always said here, you cannot have the 0 current. So then you need this as small as possible. So this on and off current will determine the circuit performance. That's why we care about that. So for the on current parameter here, this one, as we discussed later in the lecture maybe 12 on the CMOS inverter, then you will see that this on current will determine the circuit speed, how fast you can run the circuit. And the off current, today we are discussing this subthreshold off current, is also important. Why is that? So let's look at the transistor. Let's draw the symbol here. So on current, by definition here, is when the gate voltage is VDD, the drain voltage is VDD. So this source is ground. This gives you the I on. I off, okay, is you have the drain VDD and the gate 0 to ground. So this gives you I off current. So we will discuss I on current impact the circuit speed later. But today we talk about the I off, which is this subthreshold. Why would this I off matter? Because here, even in this transistor, you see that you are conducting the current from the drain to the source, even the gate is 0. So this current is consuming the power, because you know the power is VDD times I off. This is so-called leakage power. Why? It's like the transistor is leaking over time. So you know the power is voltage multiplied by the current. So you are consuming the leakage power of the transistor, even when the gate is 0. And then you ask me why this is important. Then I will tell you this is very important. This is the reason why the processor is consuming the power even in the sleep mode or standby mode. That's why in your smartphone you are doing nothing. Okay, you are not running any apps, but your battery is still being drained over time because of this. Okay, this is the reason. Even in the standby mode or sleep mode, you are doing nothing. You are not running any apps. The software programming are not running at all. As long as you power up your chip, you are consuming the power. And this is the reason. So to minimize this leakage power, then the foundries will offer different transistor technologies. And they are going to re-optimize like the doping and the gate capacitance and the geometry parameters, try to minimize the I-off current, because this is not what you want. And then they can offer this so-called low-power technology platform, try to minimize the I-off. But often the case is that when you reduce I-off, the I-on will also reduce. So there's a trade-off in the design. So if you want your circuit to be lower leakage power, you may sacrifice the speed of your circuit, because the clock frequency will be reduced as well if you use the low power technology, where the I-off is engineered to be small. That means the on current will also reduce. The clock frequency you can run will also reduce. So if you want to maximize your performance, like the clock running as fast as possible, then the foundry will also offer this HP process for you, that is high performance technology. In that case, then the on current will be boosted, but the off current will also be much larger. So you are going to trade off between the on and off characteristics here. So that's why this is important. Okay, any questions?